So chapter 13 is about something called simple harmonic motion. The first thing we want to do is just define what does that mean, because it's a very specific type of motion. So if I have a ball here, and I just bounce the ball, you'll note that the ball, or at least the way I have it happening here, or before I messed up, it was hitting the ground in regularly repeating intervals. That's not simple harmonic motion. That would be something that we would call a periodic motion. Periodic just means regularly repeating. There's no other constraints on it. So anything that is regularly repeating is periodic. The most important thing about a periodic motion is that it has a consistent period or amount of time that the cycle takes, right? So the notion of a period, and we're going to use a kind of scripty or the weird capital T here, and this is the time per cycle. And for something to be periodic, we want the period of the thing to be constant. So d capital T, d little t, we want that to be 0 because we don't want the period changing over time, which is kind of weird, like how a time changes over time, but whatever. All right. So the next thing is, well, what's going on here with this bouncing ball? Well, in the bouncing ball, what we have here is the force of gravity is acting downwards, pulling the object downwards. It accelerates down towards this position, which is a position of lowest potential energy. Then it hits the ground, and the forces change, because while it's in contact with the ground, not only is there a force of gravity, but there is a normal force. The force of gravity is still constant. The normal force is changing over time as it compresses and then springs back up. Then it's in the air, and the force of gravity takes over as well. So the force of gravity is constant in this time period, and when it's in contact here, a different force acts. And that's part of why this is not a harmonic motion. So let me give you an example of a harmonic motion then. A harmonic motion would be something like a pendulum. So if I've got a pendulum and I pull it back, it swings through its motion. Now, a harmonic motion here is periodic because this thing is going to take a certain amount of time to go back and forth, back and forth, back and forth, back and forth, right? So harmonic is a subset of periodic, right? In fact, I hope what you can see here is that what we're doing is we're going to have, if this is the Venn diagram of the periodic motions, harmonic motions are a subset of the periodic motions, and then simple harmonic motions is yet again going to be a subset of the harmonic motions. So here, an interesting thing about the harmonic motion is, well, if I move this here, why does this object go back to this position? Oh, well, this point here is a stable equilibrium. It's a point of minimum potential energy. And all harmonic motions oscillate about a point of stable equilibrium, right? Some place of lowest potential energy. And I'm not going to say it has to be gravitational potential energy, just some potential energy. So that's definitely an aspect about a harmonic motion. So why is this unstable? Well, it's unstable because at this position, force of gravity is acting downwards, but really what's important is if I draw in everything else, I've got the x component, or really what it is the tangential component of the force of gravity, and then this is the radial component of the force of gravity, that as this angle changes, so does FGT. And notice as this angle changes, which is the same as this angle here, that the tangential component of the force of gravity gets larger and larger. And so that's going to be an aspect of harmonic motion. Harmonic motion is going to be one where a restoring force exists that points toward the stable equilibrium. Okay? Now, here, gravity is a restoring force that points towards the stable equilibrium, which is here at the ground. But here's the thing where the gravity force here is different than what's going on here. Notice it's not the entire gravity force, but just this component, and that component increases as I move away. And that's an important aspect of something that's in a harmonic motion. And really what it is that makes it harmonic is that the magnitude of that restoring force, right, must be proportional in an increasing manner with the displacement from equilibrium. Meaning, the further, this is probably easiest to do in a polar coordinates. So the larger this theta is, the greater FGT is. And that's important here. So there's an increasing relationship between theta and FGT. If you don't want to do it in terms of theta, we could do it in terms of arc length. The larger this arc length is, the greater that FGT is. It's just easier in terms of theta because we know that FGT here is going to be FG sine of what that angle of deflection is, depending on how we, in terms of magnitude, we'll just say. All right, so a harmonic motion, so that means that this motion is not harmonic because the force of gravity here doesn't change based on the height. So the displacement from the equilibrium position doesn't affect the magnitude of the restoring force. This could never qualify as a harmonic motion even though it's periodic. Okay, so harmonic motion. So then the question is, well, what makes something a simple harmonic motion? Well, let's go down here where we said that the restoring force must be proportional in an increasing manner with the displacement from equilibrium. Okay, well, what is the simple increasing relationship? And then hopefully what you're saying is that is a direct relationship. And that is the main thing about a simple harmonic motion, as SHM, is that there exists a restoring force that is directly proportional to the displacement from equilibrium. Okay? And notice it's displacement from the equilibrium position. I'm going to write the word position in there. So there exists a restoring force that's directly proportional to the displacement from the equilibrium position, and obviously that restoring force, in the same thing as a harmonic motion, the restoring force must point directly towards the equilibrium position. So that has a couple of implications. If the restoring force has to be directly proportional to equilibrium, that must means that the acceleration must be directly proportional, or rather it must be directly proportional to that displacement as well, since the acceleration is just going to be the restoring force divided by the mass, and the mass is just what it is. So in simple harmonic motion, the acceleration has to be directly proportional to the position from equilibrium. Now I'm going to just keep this in vague terms here because there's lots of different position variables. The other thing is, remember, these are two vector quantities. Not only must it point directly, not only must be directly proportional, it's always got to point towards the equilibrium position. So if we go back here, if I'm displaced to the left, that means the acceleration must be to the right. And if I'm displaced to the right, the acceleration must be to the left, meaning that the acceleration is always going to be in the opposite direction from the equilibrium position as the position of the object with respect to the equilibrium position. So this equation assumes that we define the position function to equal 0 at the stable equilibrium point. Okay? So that's that. Now, why am I being all sorts of vague here? Well, what is acceleration? That's probably a better way to say it. The acceleration is the derivative of the velocity function, right? So dv dt, but what velocity is that? Well, that velocity function has to be the velocity function associated with this position function. What do I mean by that? Well, remember, what's dv dt? dv dt is ddt of a position function, right? But there are a lot of different position functions. I could have a position function along the x-axis. Fair enough. Then my position function here is x, right? Or I could have a position function along the y-axis. That's y. Or I could have a position function that is along the tangent, and then this is a theta, or a position function along the radius, and that's an r then, right? So there could be a lot of different ways of doing this. So really what this has got to be is, breaking this down, that the second derivative of some position function, oh, sorry, that should be time, right, has to be directly proportional to the negative of whatever that same position function is. So if this is an x, that's d squared x vector dt squared has to be directly proportional to negative x vector. If that's theta, then d squared theta vector dt squared is directly proportional to negative theta. Just one more. I'll do another Cartesian. D squared y dt squared is directly proportional to negative y. That's what that's going to look like. And so how do I take a function like this, or a proportionality like this, and turn it into an equality? The proportionality symbol comes out and we pick up a constant. We'll talk about what that constant is later, but this idea is the main idea because it's going to be related to something that we're going to call the characteristic equation of simple harmonic motion. We'll come back to that. So that's the basic theory behind what you need for get simple harmonic motion, but let's make this more physical, more tangible. In what situation would we get a simple harmonic motion? Well, hold on a second. The pendulum is not going to be a simple harmonic motion because if you think about it here, the acceleration along this axis is not going to be proportional to theta, but the sine of theta. We'll come back and solve that later and figure it out. So I need a force that's directly proportional to a position, not one that's position squared, or the sine of position, or the cosine of position. So hopefully what you've thought of is a spring, because a spring force, the spring force is magical, because its equation is, if that's a spring force vector, it is negative k, some constant, and then we've been using x, x, I hat, right? But remember, that could also be negative k, y, j hat, whatever it is, where just x or y are just some position functions where x equals 0 at the natural length of the spring. Right, that's the way that is derived. Y is equal to 0, right? Those are just definitional arguments when we're talking about the spring, but that seems to do some really nice thing for us because I have a force that is directly proportional to the position from equilibrium, and the force is always in the opposite direction as the displacement from that position of equilibrium position. So that meets everything we need. So let me introduce something that we're going to call the simple harmonic oscillator. Okay. Now, I'm going to make an argument here in this first video, and we're going to leave it at that. That's just very empirical, and we're going to make a lot of logical jumps. We'll come back and we'll formally mathematically prove this in the next video. So, simple harmonic oscillator is a really fancy name for a point mass on a spring. And that spring, by the way, is a massless spring, right? So it doesn't really exist, but we'll do it. So the simple harmonic oscillator, or as all the cool kids call it, the show. There it is. So let's come see the show. Haha. Right. So here's what we're going to do. We are going to look at a mass on a spring, and I'm going to do a series of drawings on the next piece of paper, but just to keep this nice and simple, just so I can outline what my process is. Let's say we attach the spring to a wall, okay? And then we're going to put a mass on the end of the spring. Now, we said that this is technically just a point mass, but I'm going to draw it as a box just so you don't think something weird is floating out there. But we're going to pretend that the point mass is just this red dot right here. Technically, I should make it at the center of mass of this object, but we're just going to use this point here because it'll make it a little bit easier to deal with. Right, and the first thing we would do is we would come over here and put in our potential energies, right? So this is where U sub S is equal to 0, because I'm going to define this as x equals 0, and then we're going to make a declaration. Let's say to the right is positive. Why? I don't know. We just got to make a declaration just to make it work, and we'll kind of go from there. Okay, and so what we're going to do is this, well, this thing will clearly not oscillate. So what we're going to do is some outside force is going to do work on the system, pull the system over to the side some distance, right, and then let it go. And then we're going to watch its motion. Now, clearly what's going to happen is this thing is going to speed up, get to this point, and then start compressing the spring, slowing it down. It's going to stop, then it's going to speed up, get to this point, then slow down, and then stop again. So it is going to oscillate. We know that it's going to be in some sort of periodic motion just from our experience with this. But what we want to do is analyze those important points. So what we're going to analyze is the point of release, the point when it gets back to the equilibrium position, how far it gets over to the side over here to the left, back to the equilibrium position, and then to where it started. And we'll ask the question, does it get back as far as it went? Now, just to make this nice and simple here, for the sake of this, we will say that this ground is frictionless for now. Later, we can talk about what happens if there's friction, but that's the basic setup of our system. So I'm going to draw a series of pictures, and then we're going to describe what's going on, and then we're going to make a chart, and then kind of come to some conclusions. So this is going to be my first position. I'm going to call that 1. And I'm actually going to draw 5 positions just because I want to have, I should probably have gotten a ruler because that was pretty sketchy. I want that to be a flat line, and it wasn't a flat line. The reason why I want to do this, folks, is because 5. I want to put the equilibrium position of the spring down all of the drawings just so that we can see comparatively what's going on. And so we said here that position 1 is how far over it's been stretched and released. So the conditions here is the velocity at 1 is 0 because it's just been released. We're not going to talk about how it got to position 1, but its initial position when we encounter it is over here at the start. We said to the right is positive, and let's say that we pulled it over a certain position. If this is x equals 0, we'll say x at position 1 is positive a. I don't know, I just randomly picked a, capital A. I wonder why. And then we said that position 2 is going to be as the spring gets when this point is back at the equilibrium position. So I'm just going to draw that here. Okay, and then we'll draw the box there. All right, now what's going to be true about the motion at this point? All that I know is at this point that this box is going to have a velocity at position 2 that's going to be like this to the left. So I know it's going to have a negative velocity. What else do I know so far? What do I know? I know that x2 is just going to be equal to 0. That sort of defines what that position is again. And we'll talk about what that velocity is. Well, actually, let's talk about that right now. So let's talk about what happens from here to here. Well, At position 1, I know in terms of forces, if I draw a free body diagram for this, I've got the spring force acting like that, I've got the normal force acting up, and I've got gravity acting down. Now, I don't particularly care about these forces, but I said free body diagram, so I wanted a complete free body diagram. All right, so what's true here? Well, if I do a sum of forces equation, sum of forces in the x dimension is equal to max, okay? Well, here, let's see, what do I have? If I was to write a sum of force equation, I just have the spring force. So I would put in negative Fs, right? No, hopefully you caught me there. The spring force is one of those forces that has internalized negatives, so I just put in Fs, is equal to max. And now I can put in negative Kx is equal to max, right? So what do I see here? What I see here is that at position 1, because, well, I can actually come up with an expression for the acceleration here. So the acceleration must be equal to, so a at 1 is equal to, well, negative k, well, x at a is positive a, so that's negative k, capital A, over m. There we go, nice and simple. All right, cool. So now I know that this thing is a negative acceleration, so it's accelerating to the left from a velocity of 0. So that means that in this segment, because the object is traveling to the left and the acceleration is to the left, that it's speeding up. So it speeds up as it goes from 1 to 2. But what's happening to the acceleration as I go from 1 to 2? Oh wow, the magnitude of the acceleration is decreasing because the displacement from the equilibrium position is decreasing. So I have a decreasing magnitude of acceleration, but the velocity is always speeding up because the acceleration and the velocity are in the same direction. So the way to think about this is if you were to describe the velocity over time from 1 to 2, you would say the velocity is speeding up, or really we would say the velocity let's say the speed is increasing, but it's doing so decreasingly, right? Increasing decreasingly, since the acceleration is getting smaller over time. Remember our increasing, decreasingly, increasing, increasingly, and all that good stuff? Yep, it is back. So since our acceleration is decreasing in magnitude, our velocity's increase is going to decrease in magnitude as well. Now, why did I not say the velocity is increasing decreasingly? Well, because in a sense, that's not really appropriate to say, because the negative, the velocity is getting more negative over time because it's heading towards negative infinity. So, but like when we think velocity is decreasing, you naturally think slowing down. You don't think is moving, the number is going towards negative infinity. So I wanted to use the speed term here. We have to be very careful with our ideas. Now, when I get to position 2, though, I think it's pretty easy to see that at position 2, x is 0, so the acceleration is also equal to 0. So this thing has stopped accelerating when it gets here. Oh, so it was accelerating, or it was speeding up all the way to here, and then it stops speeding up. That must mean that at this position, it has achieved a maximum velocity. Well, that should make a lot of sense, because this point here is the point of minimum potential energy, so it has to be the point of maximum kinetic energy. So we can use that notion then to find the speed at position 2. So here we go. The energy at position 1 is equal to the energy at position 2, because the work non-conservative is equal to 0, right? There's no friction, spring force is conservative. So what form of energy do I have here? I have spring potential energy. So I have 1/2 k x squared. And the x at position 1 is a. So 1/2 k a squared is equal to 1/2 m v at position 2 squared. So we can see the halves go away, and I'm left with then the speed at position 2, and I probably should have left more room here because 3, 4, and 5. The v at position 2 is going to equal the square root of k over m a squared, or just a k over m, and that was plus or minus. And then here, because position 2 in my declaration, I'm going to say it is a minus. Great, so I know what the speed then at this position is. And that speed is the maximum speed this thing is going to achieve. Okay, cool. So, next, position 3. We know that the spring is going to compress, and at some point here, it's going to stop, right? So, position 3, we're just going to define to be when it stops. So we know the speed at position 3 and the velocity at position 3 is 0, because that's when I care about it. So let's talk about what happens from here to here. I know the velocity was to the left over here, but if I draw a free body diagram, the spring force is now opposite that. So this object is going to be slowing down as it comes here. If I look at this expression here, notice that for every position from 2 to 3, the x would be negative, right? I would plug in a negative some odd, which would make this positive, so the acceleration is a positive thing in this region, even though the velocity is negative. Cool, it's slowing down. What's also happening to the velocity? Well, it's slowing down, but the acceleration is increasing as x gets bigger. That means that it is slowing down increasingly, or that from 2 to 3, the speed is decreasing increasingly. So the speed decreases increasingly. All right, cool. Now, how far, well, let's actually say then, how far over does it get? Well, how far over does it get? Well, let's just do energy conservation. Energy at 1 is equal to energy at 3. Work non-conservative is equal to 0. So once again, I've got 1/2 k a squared is equal to, well, over here, I've just got potential energy to a spring because it's stopped. 1/2 k x3 squared. Oh, okay, well, this is pretty easy then. x3 has got to be plus or minus a then. And then I'm just going to accept the negative root there. So it stops just as far to the left as this thing started to the right, okay? So I know x3 then is negative a, and that allows me to get then what a3 is. a3 has got to be negative k, negative a over m, plugging into this, which is just k over m a. All right, cool. So we've got that. And that's a result we should have expected just based on our physical experience. Now, coming back then, it's going to go to this point, and at some point it's going to pass through the equilibrium position. We know the velocity is to the right now. Oh, hold on a second. This energy conservation statement is the same then, E1 to E4. So solving for V4, it's still the same thing, but now we would accept the positive root. So here, x4 is equal to 0, therefore A4 is equal to 0, but V4 is equal to a positive a square root of k over m. And then hopefully you understand that 5 is going to just go back to position 1. So we just then can repeat the cycle. So everything that's true about 1 is true about 5. And the interesting thing about this is throughout this motion, the acceleration is constantly changing. The velocity is constantly changing. Well, actually, let me rephrase that. The acceleration is continuously changing. The velocity is continuously changing, and the position is continuously changing. Why that change of phrase? Right? Well, because we're going to find out that these graphs are not lines, right? So I wouldn't want to say constantly because that might make people confused. So let's see what we have here. If I then look at x, v, and a, and let's put this into chart form, 0, over the 1, 2, 3, 4, and 5. Just to make my life a little easy. I know I started out at positive a, 0, negative a, 0, positive A. Here, V, I went and I started at 0, and then it became negative A radical K over M, 0, positive A radical K over M, 0. And then here I had negative K over M A, 0, positive K over M A, 0, negative K over M A. That's interesting. That K over M term pops up quite a number of times. Here it's the square root of K over M, or here it's the square root of K over M squared. It's so interesting that that popped up. So, what do we have here? Well, if I was to graph the position function as a function of time, right? 1, 2, 3, 4, 5, there we go. And that's time. First off, the time from 1 to 2 compared to 2 to 3. I've now marked these off as equal time intervals, but that probably bears some discussion. I would assert that the time it takes to go from 1 to 2 is the same as 2 to 3. Why? Well, hopefully what you've got is this thing undergoes the same acceleration from here to here, the same delta A as it does from here to here, right? Just here it goes from some sort of negative value to 0, from 0 to the same positive value, right? And the way that the acceleration changes is identical as well, right? So the average acceleration in this time period is equal to the average acceleration in this time period. We also showed that the delta V in this time period is the same as the delta V in this time period, and the delta X in this time period is equal to the delta X in this time period. So because all those average quantities are the same, we could make the assertion then that the time to go from 1 to 2 is equal to the time to go from 2 to 3. So that's how I can draw this graph. So now if I plot then, if this is A and this is negative A, I'm plotting this, 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 this. Oh, hold on a second. I'm an idiot. 1, 2, 3, 4, 5. I don't need this. Okay, cool. And then 5. So that's the same thing. Now, would I want to connect these with straight lines? Well, remember, the slope of this line is the velocity. If I connect these with straight lines, that must mean that the velocity is constant. But we showed that the velocity was changing continuously, so I've got to definitely have curves here. But the question is, do I want a concave up or a concave down curve? Oh, it's a position versus time graph. That must mean that the concavity of the graph in that time period has to be equal or is indicated by the acceleration. So notice here in region 1 to 2, the acceleration is negative. That must mean I need a concave down graph where the slope is getting steeper, right? But it gets steeper in a decreasing sort of way. The slope changes a lot from here to here, and from here to here it doesn't change that much. In the next section, I need the slope is going to, the speed is decreasing, so the slope is getting flatter, and it's doing increasingly. So in other words, small changes in slope to big changes in slope. But what's the acceleration in region 2 to 3? Well, that is positive, so it's got to be concave up. And then if we continue along, concave up, and then concave down, and the slopes are doing everything I need them to do. Very clearly, the slopes here are negative and getting steeper. Here they are negative and getting less steep. So in other words, I'm speeding up to a maximum and then slowing down to 0. And then likewise over here. Beautiful. So you're looking at this, folks, and hopefully by now you're thinking, well, what function does that look like? It kind of looks like A is equal to A cosine of t. Now, I'm just going to put something here because let's talk about what goes here. What is the name of the thing that goes here? Hopefully you remembered that this is called the frequency. That's what they call it in math class. They're correct, they're accurate, but they're not precise. What actually goes here is something that's called the angular frequency. Because frequency in physics, script EF, is equal to the number of cycles per second, right? That's what a hertz is. But what I need here is this thing has got to either end up in degrees or end up in radians so that I have the right units here for the cosine function to act upon. So we're going to want this to be not the number of cycles per second, but a number of radians per second. Radians per second. I wonder if we know something that's radians per second. Oh, we do. That is omega. Now you're going to say to me, hold on a second, Vaughn. Omega is angular velocity, not angular frequency. And to you, I'm going to say it's both, right? So this is known as the angular frequency, the number of radians this thing goes through per unit second, and we have then a function that fits the data, okay? Great. So now let's go on to the velocity graph. Oh, hold on. Actually, let's take a side. Angular frequency, number of radians per second. Well, omega, number of radians per second, that's got to be equal to 2 pi. So if I go through 2 pi radians, how many seconds does that take? Well, 2 pi is 1 complete cycle. So what I would need down here in the bottom is the period, because that is the amount of time for 1 cycle, right? So the thing in front of the t in the argument of the cosine function can help me find the period or the periodicity of that function, okay? And in terms of linear frequency, we can see then that 1 over period is linear frequency, so omega is just equal to 2 pi times the linear frequency, just so that we can see all those equations together. All right, cool. So next, I'm going to keep the same sort of divisions here. And I've got, okay, apparently this thing goes from, we've got a radical k over m and negative a radical k over m. So what's that going to be? Well, I'm going to go from 0 to negative a radical k over m to 0 to positive to 0. Same arguments here. We know that the speed is going to change in a changing way. And so I know that the acceleration in this time period is negative and it is getting smaller. So that means the slope has to be negative and getting smaller. So that is something that looks like this. In this region, the slope has got to be positive and getting larger because that's what the acceleration is doing in that region, so on and so forth. Once again, we have a curve. And if you're looking at that, you're like, oh, that's a very familiar curve. Remember, this is the velocity as a function of time. It looks like the velocity then is equal to, well, the height of this is a radical k over m, but this looks like what? Oh, this is like a negative sine function, doesn't it? Now, notice here, the periodicity of the velocity graph is identical to the periodicity of the position graph. So that means that whatever the angular frequency of this function is has to be the angular frequency of this function. So that's identical. So we'll come back to that later. Okay, cool. So negative sine graph. Oh, I'm an idiot. Of course it's the negative sine graph. Why of course? Because velocity is just the first derivative of position, and the first derivative of a cosine is a negative sine. Of course, we'll come back to that. Because I want to draw one more graph using this. So let me see if I can get all of this on. And that is the acceleration as a function of position. Okay. So if I look at that, let's see, it looks like I'm going from negative k over ma, and then positive k over ma here. And I'm going negative 0, positive 0, negative. And we can sort of make the same arguments, I think, by now people kind of see what's going on. I'm not going to belabor the point because I've already belabored the point. So if I'm saying what type of graph is this, got it. It is a negative cosine graph. So we know that the height of this is equal to a k over m cosine, and it's got the same periodicity, so omega t, and there we go. Okay, great. So I've got that. So there you go. Well, hold on a second. So how would these graphs be different then if rather than initially pulling it out to the right, I pushed it into the left? Oh, okay, well, this would start out negative a, 0, positive a, and so on and so forth. So in other words, that would start here. We'd just shift the graph over and I'd get a negative cosine graph. But then this would be a positive sine graph, and then this would be a negative, or rather, excuse me, a positive cosine graph. So where you start this thing matters. I could also encounter this thing. What happens if I started at t equals 0? I knew the thing had a velocity and it started here. I need to adjust these functions here to account for that. So what I need here is something in the argument of the graphs that allows it to shift over. And so what we're going to see here is x is equal to a cosine of omega t. And what I'm going to do is I'm just going to put in a shifting factor here, and it's called phi, something we'll call a phase angle. Right? So if phi is 0, I start exactly how we did. If phi is pi, I start at a different position. But that allows a more generalizable function, but I can still use these as the basis for what I have, but then that phi allows all these different positions. We're almost done with this, folks, so no worries. Negative a k over m cosine of omega t plus phi. Okay, cool. Now, we did say that a had to equal dv dt and v has to equal dx dt. So this is the last bit for this. Ready? So if that's true, if I took the derivative of this expression, what do I get? Well, I get dx dt would be equal to, well, the a would do what it does. If I took the derivative of this function, I would have to use the chain rule in order to do this. So I would end up with a negative omega sine, and then the periodicity would stay the same, omega t plus phi. The phi is a constant, so nothing would change there. Or negative a omega sine of omega t plus phi. And then if I take the derivative of that again, so dv dt, that would give me, of this, negative a omega squared cosine of omega t plus phi. Hopefully you see what's happening there. Apparently for this function, omega is equal to radical k over m, right? So, oh, okay. So this is very specific to the simple harmonic oscillator then, because these are general equations. I don't know what the force is that's causing these to happen, but this k is very much a function of the fact that it's a spring, and the m because there's a mass on the end of it. Well, what can I get out of that? Well, okay, cool. That means that simple harmonic motion, here are the characteristic equations. Any simple harmonic motion has got to have this as its pattern. And a of t is equal to negative a omega squared cos of omega t plus phi. Okay, so these are the basics. And if I then go back to what we had before, notice here, let's just go very specific to the simple harmonic oscillator. We said that A was equal to negative k over m x. Now we just said that omega was equal to radical k over m. So this was equal to A is equal to negative omega squared x. Yes? Here we go. The second derivative of x with respect to t squared is equal to negative omega squared x. Does that look familiar? All right, hopefully it does, because it's the point of the entire lesson. Remember this? The second derivative of a position function was directly proportional to the negative position function. And I said that to turn a proportionality into an equation, you needed a constant. Apparently that constant is the angular frequency of that simple harmonic motion squared. So this equation here, folks, is known as the characteristic equation of simple harmonic motion. If you can prove that the acceleration of an object is equal to negative some constant times a position function, you've proven that object's in simple harmonic motion, right? Here, the simple harmonic oscillator fits the definition. So a couple of things on this, and then we'll call it a day. So omega, we said omega is equal to 2 pi over the period is equal to radical k over m. Therefore, the period of a simple harmonic oscillator is 2 pi radical m over k. See if that makes sense. A more massive object is going to take longer to go back and forth. A stronger spring is going to take less time to go back and forth. Boom, there it is. You'll notice that the maximum speed of the simple harmonic oscillator, well, the maximum value of the sine function has to be equal to 0, or excuse me, sorry, the maximum value of the sine function is 1. That means that this is equal to a omega, where the max speed is a radical k over m, and then the max acceleration has got to be a omega squared, or a k over m, okay? And then for the simple harmonic oscillator, in terms of energy, I'll just kind of like continue that over here. The energy of the simple harmonic oscillator at any point is the sum of its kinetic energy plus potential energy at any specific point. So that's the speed at that point. That's the position at that point. But what is the total energy of that? Well, we know that when the speed is equal to 0, x is at its largest point. So we're going to define that as being the amplitude of the idea. Amplitude, right? And so A is amplitude. The amplitude of the simple harmonic oscillator determines the total energy of the system. Notice though, the period does not change. Oh, that's because the max speed gets bigger if the amplitude's bigger. So even though it's got a further distance to go, it goes faster. And so that, folks, is a very empirical derivation of simple harmonic motion and the simple harmonic oscillator. The next video is going to tackle this entirely from a mathematical perspective, and we're going to learn how to solve second-order homogeneous differential equations in order to do that. The third video is going to look at other systems rather than the simple harmonic oscillator.